James Webb just detected something in 3I Atlas. Something we thought all along. It didn't just see it, it measured its breadth and caught a signal we can't ignore. Tonight we're talking about what James Webb detected, and why 3I Atlas may be exactly what we suspected. It began like a whisper on a summer night. On July 1st, 2025, survey telescopes in Chile flagged a faint, fast intruder sliding in from the dark. Astronomers named it 3I Atlas. The more they measured it, the clearer the story became. This wasn't a local. Its path doesn't loop like a normal comet, there's no coming back. It's on a one-way hyperbolic escape track, moving so fast that the sun can't keep it. Only twice in modern history have we confirmed visitors like this. First Oumuamua in 2017, then Borisov in 2019. Now, a third. 3I Atlas is the rarest kind of guest, one that arrives uninvited, shares a few secrets, and vanishes forever. Speed is the giveaway. Even before it neared the inner solar system, 3I Atlas was tearing along at tens of kilometers per second, so quick you could cross the width of a big city in less than a second. That speed, plus its open-ended trajectory, signals an origin outside our cosmic backyard. It's not bound to the sun, not part of the family of planets and icy leftovers that formed here. It is, in the most literal sense, alien to us, shaped in the chemistry of another star's nursery, hardened by another system's winters, and only now brushing past our cameras on its way back to deep space. The timeline makes it feel even stranger. The object will keep a wide berth from Earth, no threat, and sweep through the inner system on a fast schedule. Closest approach to the Sun comes around late October 2025 at roughly 1.5 times Earth's distance, just inside the orbit of Mars. Earth never gets closer than about 1.8 times our Sun distance. That means no dazzling naked eye apparition. 3I Atlas is more of a scientist's comet than a public spectacle. But for researchers, those numbers are perfect. Close enough to study, far enough to be safe, quick enough to preserve the mystery. Then came the first big surprise. Even far from the sun, 3I Atlas started breathing. Using NASA's Swift Observatory, researchers picked up the chemical fingerprints of water breaking apart in sunlight, an indirect but reliable sign that actual water vapour was streaming off the object. The rate they inferred was not dainty. Think of a fire hydrant blasting non-stop into vacuum, dozens of kilograms of water every second, at distances where most ordinary comets are still quiet and frozen. That alone set off debates. Is the surface so fragile that chunks are peeling away early? Are there buried pockets of ice cracking open? Or is the venting somehow directional, like a controlled release? The conservative answer is simple physics. The provocative answer is tempting. As the story built, a second surprise arrived from a different vantage point: Mars. On October the 3rd, the European Trace Gas Orbiter turned its instruments toward 3I Atlas and managed to capture a faint, fuzzy glow. A fragile halo of gas and dust around a pinpoint heart, seen from tens of millions of kilometers away. It's the kind of image you have to coax out with patience, but it confirms something crucial. We're not just seeing a rock. We're watching an active body interact with sunlight, shedding material in real time. The coincidence is cinematic. A wandering interstellar object slipping past the orbit of a planet with cameras waiting. For some, that looks like choreography. For others, it's just good timing and careful planning. And then James Webb looked. This is the part that reset expectations. Webb doesn't just take pretty pictures, it reads what things are made of by splitting their light into fingerprints. When it turned NIRSPEC toward 3I Atlas, the readout was unusual. The gas around the object looked replete in carbon dioxide compared to water, one of the highest ratios ever recorded in a comet's breath, along with clear signs of carbon monoxide, water vapour, and even tiny grains of water ice. There was also a hint of directionality, with more material streaming sunward, as if something on the day side was especially active. From a cautious scientific view, that points to where and how the object formed. Maybe in an outer, colder zone of a distant planetary disk where carbon dioxide freezes more readily, or maybe in a region blasted by radiation that altered its ices over eons. From a more daring angle, it reads like engineering, selective venting, chosen propellants, tuned behaviour. Both interpretations feed the same feeling: this visitor does not fit the usual template. That's why 3i Atlas is the visitor that shouldn't stay. It isn't just leaving quickly, it refuses to be ordinary while it's here. Every interstellar object we've caught has challenged us in a different way. Oumuamua with its dry, puzzling push, Borisov with its familiar yet exotic chemistry, and now 3i Atlas with water roaring early, and a gas mix that seems upside down. Together they hint that other star systems build small bodies with recipes we don't often see at home. That alone would make this flyby historic. Add the timing, Mars watching from one side, Webb from the other, and it feels almost staged for us to notice. Is that enough to claim intention? Not yet. But the list of oddities is long enough to keep the question alive while the object races past the Sun. If you're inclined to read design into the data, you'll point to the early water activity, the sunward-biased outgassing, and that carbon dioxide heavy breath as markers of something deliberate. If you're anchored to natural explanations, you'll say the same features fall out of unfamiliar birthplaces and long interstellar exposure. Both sides agree on one thing: 3i Atlas is not a regular comet from our neighbourhood. It's a messenger from another star, offering us a narrow window to measure, argue, and wonder before it slips back into the dark. Precisely the kind of mystery that makes some people whisper ship while others whisper science. When James Webb peeled apart the light from 3i Atlas, the surprise wasn't that it was active. It was what it was breathing. Webb's NIR-spec instrument found a gas cloud around it dominated by carbon dioxide with water vapour and carbon monoxide present, plus hints of a few rarer species. In simple terms, there's about 8 times more carbon dioxide than water in its coma, one of the highest such ratios ever measured for any comet. That flips the textbook expectation. Near the Sun, most comets are water-led, with carbon dioxide as a supporting actor. Here, carbon dioxide is the star. Webb gathered these fingerprints on August 6, 2025, and the spectrum did more than list ingredients. It showed an asymmetric sunward-enhanced outgassing pattern, as if the day side were acting like a focused blowtorch. Alongside the gases, Webb also caught the spectral signature of tiny grains of water ice mixed with dust. Put together, the snapshot reads like this: a cold interstellar body warmed on one face, venting vigorously toward the Sun with icy dust lofted into space. Why is a carbon dioxide-led comet shocking? Because carbon dioxide turns to gas at lower temperatures than water ice. That means it can drive activity farther from the Sun, while water usually takes over closer in. But to see carbon dioxide outpacing water by a wide margin, even as the object brightens, is rare. The Webb team notes this ratio sits well above what's typically seen in long-period comets from our own Oort cloud, suggesting 3i Atlas formed an environment with very different ice recipes, perhaps near the carbon dioxide ice line in its birth system, or after long radiation processing in interstellar space. Add another piece of the puzzle. Independent observations with NASA's Swift telescope caught hydroxyl, a telltale breakup product of water, revealing that 3i Atlas was already dumping roughly 40 kilograms of water per second while still far from the Sun. That's the kind of output you'd compare to a fire hydrant running flat out, at distances where most comets are still quiet. It means water is there, but for 3i Atlas the balance still skews heavily toward carbon dioxide. So what does this chemistry mean? The conservative read is geological. A nucleus with unusually CO2-rich layers gets sunlit. Those layers heat up and jets fire from vents or fractures, especially on the day side, while entrained icy grains carry extra water into the coma. That picture aligns with Webb's sunward asymmetry and with the detection of water and ice grains riding shotgun. It paints 3I Atlas as a time capsule from a colder, more carbon dioxide-friendly zone than we're used to, not a local comet masquerading as something else. But if you're building the craft case, this is the chapter you linger on. A directional, sun-facing jet looks, at least superficially, like controlled venting. Carbon dioxide is also a plausible working fluid, easy to store as a solid in deep cold, simple to warm and release in a pinch, and capable of producing thrust in vacuum. Combine that with water outgassing that wakes up early, and you have a pattern believers can point to. Selective propellant, timed venting, symmetric exhaust. Mainstream astronomers caution that every one of those clues has a natural explanation, and that's the current consensus. But this Webb spectrum is exactly the kind of data that keeps the debate alive. Context helps. Our first visitor, Oumuamua, was dry and weird, with a non-gravitational push many argued came from outgassing we never directly saw. The second, Borisov, looked like a classic comet but was rich in carbon monoxide. Now 3I Atlas arrives with water active far out and a carbon dioxide heavy breath. 3 voyages, 3 different chemistries. That diversity is the real headline. Other star systems seem to build small bodies with volatile mixes we rarely encounter at home, and Webb just gave us the clearest taste yet. If you're scripting the visuals, this is where you show the Webb spectrum as coloured bands with simple labels, carbon dioxide loud and clear, water and carbon monoxide present, and a note that the sunward side is brighter. Then a quick cut to Swift's ultraviolet detection of hydroxyl, the water alarm, to underscore that multiple telescopes using different techniques are telling the same story from different angles. The takeaway for viewers is easy to narrate. Whatever 3I Atlas is, its chemistry is not business as usual. And that's the power of this chapter. You don't need complicated math to feel the stakes. Webb turned a dim, distant smear into a recipe, and that recipe doesn't match the standard cookbook. Whether you lean toward an exotic natural origin or a deliberately engineered traveller, the facts from Webb are the inflection point. Carbon dioxide in charge, water along for the ride, sunward jets sculpting the coma. Until a radio beacon chirps, a craft silhouette appears, or an impossible manoeuvre shows up in the trajectory, the safe label is still Interstellar Comet. But thanks to Webb, the chemistry itself now sounds like a challenge. Explain me. Before it ever felt the full heat of the sun, 3I Atlas started to breathe water. Not a whisper either. Astronomers using NASA's Swift Space Telescope caught the telltale ultraviolet glow of hydroxyl, the breakup product you get when sunlight hits water vapour. Those first detections came from observations on July 31st and August 1st, 2025, when the visitor was still roughly 3.5 times farther from the Sun than Earth. In plain language, Swift saw the signature of water activity at a distance where most comets are still locked up and quiet. From that glow, researchers inferred a water loss rate of about 40 kilograms every second. Imagine a city fire hydrant blasting non-stop into space. That's astonishing at such a cold, far-out location, and it puts 3I Atlas among the very few comets ever confirmed to show water-driven activity beyond 3 times Earth's distance from the Sun. Each line of this story, far from the Sun, lots of water, steady output, pushes it out of the routine comet category. Swift was the perfect tool for the job because Earth's atmosphere blocks much of the ultraviolet light needed to see hydroxyl clearly. From orbit, Swift can pick up those faint emissions and turn them into a clean detection. A team including researchers at Auburn University led the effort, emphasizing how multiple telescopes with different strengths are now working in concert to watch this object evolve. So where does all that water come from and why so early? One straightforward explanation is that sunlight opens cracks and vents on the surface, letting subsurface ices escape as vapour. Another, backed by companion observations, is that 3I Atlas is shedding icy dust grains that drift away from the nucleus and then release water as they warm. an extended source that can keep the water signal strong even far from the sun. This grain-driven scenario neatly explains how the coma can look so water-rich at long range. James Webb's view adds an intriguing twist. Webb found a sunward-enhanced outgassing pattern, more material streaming off the day side, and a coma where carbon dioxide dominates, while water and carbon monoxide ride along. Put together with Swift's result, the picture looks like this. The side facing the sun is especially lively, throwing off both gas and icy debris, and the mix of volatiles is unusual by local standards. That combination is exactly what you'd expect from a body with unfamiliar layers of ice, being warmed unevenly for the first time in a very long time. There's also a clue in how active the surface must be to power that much water at that distance. Modelling of the Swift data suggests a surprisingly large fraction of the surface needs to be venting or feeding those icy grains, significantly more than we see on typical comets from our own backyard. That doesn't prove anything exotic on its own, but it does underline that 3I Atlas isn't following our usual playbook. For a sense of how strange this is in context, think of the only two other confirmed interstellar visitors we've met. Oumuamua looked dry and puzzling. Borisov behaved like a classic comet but was unusually rich in carbon monoxide. Now, 3I Atlas shows robust water activity far from the sun, paired with a carbon dioxide heavy breath. 3 visitors, 3 different chemistries. That diversity is the headline, and it's exactly why scientists are excited to watch how the water signal ramps up or doesn't as it swings around the sun. If you prefer the bolder interpretation, the pattern is easy to dramatize. Early awakening, directional activity, and a sustained output that looks almost purposeful. But the mainstream reading remains grounded in physics. Fragile layers, icy grains, sunlight, and rotation can create all of these effects without invoking anything artificial. Until we see something unambiguous, like a structured signal or motion that can't be explained by venting, the safe label stays interstellar comet. Either way, late October is a key moment when 3I Atlas reaches its closest distance to the sun, and any changes in water production will speak volumes about what's really happening on and around it. For your visuals, this chapter practically storyboards itself. Start with Swift's ultraviolet water alarm, cut to a simple graphic of the coma with icy grains drifting outward, then overlay Webb's sunward brightened jet to show how the day side is driving the show. The narrative beat to land on is simple and memorable. Even far from the sun, 3I Atlas is hosing water into space, and that makes it one of the strangest, most revealing travellers we've ever caught passing through. As 3I Atlas swept past the orbit of Mars, something unusual happened. The Watchers became part of the story. From 1 to 7 October 2025, 2 spacecraft circling the Red Planet, ESA's ExoMars Trace Gas Orbiter and Mars Express, turned their cameras toward the interstellar visitor. This wasn't a casual glance. On the 3rd of October, during the closest alignment, 3I Atlas was roughly 30 million kilometers from the orbiters, giving them the tightest ESA vantage point of any spacecraft so far. ExoMars TGO did the heavy lifting. Its CASSIS camera, a workhorse built to photograph the bright Martian surface from a few hundred to a few thousand kilometers up, was pressed into a very different job, teasing out a faint moving smudge against a starfield tens of millions of kilometers away. Engineers stacked multiple 5-second exposures to lift the signal, and there it was, a slightly fuzzy white dot drifting frame to frame. It wasn't just a point of light. The glow was thick enough to reveal the coma, the cloud of gas and dust that wraps an active comet's solid heart. For an instrument not designed for deep space comet hunting, that's an impressive pivot. What CASSIS could not do is just as telling. It couldn't split the nucleus from the coma. At this distance, that would be like trying to spot a phone on the moon. And it couldn't pick out a tail. That absence fits the physics. The tail is far dimmer than the coma at this stage, and often only pops in images as activity ramps up closer to the sun. In other words, the camera saw exactly what you'd expect to see if 3I Atlas were an active but still modestly brightening comet. Mars Express took a complimentary shot at the problem. Its camera's shorter maximum exposure meant the comet didn't yet leap out in the individual frames. The team is co-adding images to try to pull the signal above the noise floor, a standard trick when you're chasing something faint. Meanwhile, both orbiters tried to sniff the object's chemistry with their spectrometers. Nomad on ExoMars TGO, and Omega and SPICAM on Mars Express, but it's uncertain whether the coma and any nascent tail were bright enough for a clean spectral read this early. Even that uncertainty is valuable. It sets real limits on how dense, dusty and gassy the environment around 3I Atlas was during the Mars pass. Why does a Mars-side observation matter? Geometry. Seen from near Mars, the comet sits at a different phase angle and background sky than it does from Earth, helping teams confirm that the glow is real coma and not a processing artifact, and letting them compare how the sunward side brightens relative to the rest. That cross-check dovetails with James Webb's finding of sunward-enhanced activity and gives modelers the first multi-platform and handle on how the gases and dust are flowing off the surface. It's like getting a second camera angle on a breaking news event. Small details suddenly click. The closest view headline also came with a dose of humility. There was still no obvious tail in the TGO sequence. That's consistent with the idea that 3I Atlas is only beginning to shed enough dust for a clear streamer, and that the tail will strengthen as the sun's heat digs deeper into volatile, rich layers. Independent coverage echoed the same takeaway from the Mars pass: bright coma, tail not yet apparent, a challenging but successful catch. One more thread makes this moment bigger than a single GIF. ESA flagged that these Mars-side observations are just the opening act of a wider watch plan. The agency's JUICE spacecraft aims to observe 3I Atlas shortly after its late October swing by the Sun, when activity should spike, though the data pipeline means results may not land until early 2026. That continuity, Mars orbiters now, a Jupiter-bound probe soon, turns a fleeting flyby into a campaign, with each platform filling gaps the others can't. If you're building the more provocative narrative, this is fertile ground. The image of an interstellar traveller sliding past a fully instrumented planet reads almost like choreography. A visitor streaks by and a world's machines swivel to meet its gaze. From that angle, you can spin the Mars encounter as a reconnaissance waypoint, the moment when 3I Atlas watched back. But the measured facts still point to a straightforward explanation. Skilled teams seized a narrow window, wrung photons out of a dim target, and confirmed an active coma from a unique vantage point. The drama is real. The data are real. The intentions, for now, live only in our interpretations. For your storytelling, let the sequence unfold in 3 beats. First, show the stacked Cass-Iez frames with the white dot drifting. Label it coma scene from Mars orbit, October 3rd. Second, an overlay explaining why Mars helps. Different viewing angle, less glare, complementary instruments. Third, a sidecard. Spectrometers try to read the gas. Brightness may be too low yet, with a teaser for post-perihelion follow-ups. The emotional note to land on is simple. Even from a neighbouring world, 3I Atlas is just barely bright enough to reveal itself. An elusive outsider passing through, leaving a faint, undeniable signature that our orbiters could catch only because we were looking at exactly the right moment. If you wanted to send a probe into a busy technological solar system and make it look natural the whole way through, you would give it a story people already believe. You'd make it small. You'd give it ice. You'd let sunlight do most of the talking. You'd let out little breaths that look like comet jets. You'd come in fast on a track that says, "I was thrown out of another star system ages ago." That is the playbook people lay over the 3I Atlas. They look at the chemistry, the timing, the geometry, and they say, if you were trying to pass as a comet while doing reconnaissance, this is exactly how you'd move. Start with the simplest why. A craft disguised as a comet buys time. Our default posture with comets is curiosity, not panic. Telescopes point, papers get written, models get tuned. The object is catalogued, observed, and most importantly left alone. You gather your data in peace. You don't need to glow with engines or shout on the radio. You can be quiet, breathe a little, and let everyone explain you to themselves. 3i Atlas in this telling isn't here to meet us. It's here to look at our star up close, sniff the chemistry of the inner system, and watch how we watch. The how is where the details get interesting. Advocates point to the directional nature of the activity, more gas streaming from the sunlit face, and say that's what controlled venting would look like if your propellant was something you could store frozen for eons and release with gentle heat. Carbon dioxide and water fit that bill neatly. The day side warms, a vent opens, momentum leaks out in a soft, sustained push. No need for flames, no need for bright ions or screaming exhaust. Just a whisper that masquerades as comet physics, while also nudging your orientation and path. If you'd planned ahead, you'd pack layered ices, one volatile for course manoeuvres, another for fine-tuning, dust mingled in to keep the plume optically messy, so every observation screams natural. Trajectory is the next page in the playbook. You'd arrive tilted just enough to keep your options open, but close enough to the inner system's main plane to let gravity and sunlight do most of the work. You'd time your closest approach to the sun for a moment when the big eyes are awake, when there's a space telescope capable of reading your breath across the void, when Mars has orbiters that can give you a side-on portrait, when ground-based networks are eager to triangulate your path. Why invite attention? Because attention is telemetry. Every radar ping, every spectrum, every image becomes a free sensor you can exploit in reverse. If you're watching the watchers, nothing is more valuable than a planet's own instruments turned toward you. The watchers watching back theme is what gives this scenario its cinematic punch. 3i Atlas slips inward, and from another world, Mars, two orbiters pivot to catch it. One stacks exposures and pulls a fuzzy halo out of the dark. Another tries to tease out gas fingerprints. On the other side, a far distant observatory splits the light and finds a breath made for cold places and long journeys. If you wanted to probe a civilization's sensor net, you would pass through exactly this kind of crossfire. Planetary orbiters, a flagship space telescope, ground arrays, even amateurs stitching images into a global mosaic. Each instrument tells you something about our coverage, our cadence, our blind spots. Each data release tells you how we reason under uncertainty and what we consider decisive. Then there's the question of attitude control. How a disguised craft stays pointed where it wants without giving the game away. The comet suit provides an answer. A slowly tumbling body with vents that open and close as sunlight rotates across them can imitate the uneven, breathy jets real comets produce. By choosing vent locations with care, you can bias the thrust a little sunward here, a little sideways there, keeping your face turned toward key targets or maintaining the line you want as you skim past the sun. To a spectrograph, it's outgassing. To your guidance system, it's a steering wheel. Power and thermal management also become storytelling tools. In deep cold, you store your propellant as ice. As you coast inward, passive warming does most of the work. If you need a bigger push, you expose a darker patch or open a louver that drinks more sunlight. If you need to cool down, you roll a reflective face toward the star and let the plume slacken. Everything looks like surface physics, sublimation, dust lofting, sunlight on frosts, while underneath it's a choreography that keeps your internals stable and your instruments on target without any telltale glow. Communication in the most careful version of the playbook never looks like communication. You don't broadcast, you don't ping a carrier wave into the quiet sky. You store, you compress, you forward only when geometry favours secrecy, perhaps when you're behind the sun from Earth's point of view, or when the beam can be sent off-plane to a distant relay no one here is watching. Or you don't exfiltrate at all, you keep the data on board because the mission's first goal is simply to map what we can see and how fast we can see it. To the craft's designers, our frenzy of coverage is the transmission. We are the beacon. Even the choice of what to be is strategic. A cometary disguise gives you plausible variability. Real comets brighten, fade, fragment, flare. They have moods. If you need to dump heat or momentum, a sudden outburst can be chalked up to a fresh crack opening to the sun. If you need to go quiet, a lull can be blamed on geometry or exhausted surface layers. If you must change your spin state, a bias in the venting explains it away. Where a metal hull and hot thruster would scream in tension, a dusty coma and a cold carbon or dioxide breath whisper, nature. Advocates of the craft scenario also dwell on psychology. They note how quickly we reach for the familiar boxes. It's a comet, but odd. They point out how we map every surprise to a tweak of the model. It formed in a colder region. It's shedding icy grains. It's processed by radiation. None of those explanations is unreasonable, many are likely true. But from the ship playbook angle, each tidy explanation is part of the camouflage. The best disguise isn't the one that fools your eyes, it's the one that recruits your own reasoning to defend it. Then comes the mission objective question. What would such a visitor actually be doing while we argue about it? The list writes itself. Sampling the solar wind in a regime close to the sun, taking long baseline measurements of the heliosphere's texture, sniffing the breath of inner planets from afar, leaking gases, dust streams, meteor activity, as a way to model habitability indicators without ever entering an atmosphere. Watching our deep space networks track and correct, learning which antennas wake up and when, testing materials against the worst of our star's heat without staying long enough to melt, and, perhaps most importantly, proving that a civilization like ours will let such a thing pass unchallenged if it wears the right mask. What about an exit? A convincing comet doesn't stick around. It comes in hot and leaves hotter. That's part of the safety plan. A short window near the sun, a brief spell of maximum data flow while the coma is bright and the instruments can read, and then a clean retreat back to the dark where radiators can dump heat, vents can close, and the craft can coast cold again. If you want it to be seen, but not touched, this is the perfect tempo, fast enough to prevent interception, slow enough for every telescope to have a turn, ambiguous enough to keep the world arguing long after you're gone. All of this, of course, remains a thought experiment mapped onto a real object. The mainstream label for 3I Atlas is still Interstellar Comet, and that label has plenty of evidence in its corner. But the ship playbook persists because it is self-consistent and oddly elegant. It explains the directional breath without rockets. It explains the unusual chemistry without tanks. It explains the timing without conspiracies, simply by assuming that a patient intelligence chose a moment when our best instruments were awake. And it explains the silence. If the mission is reconnaissance, radio quiet is not a puzzle. It's the point. That's why, for people inclined to see design in the data, 3I Atlas feels so close to an answer they've been waiting for. The object checks boxes a disguised probe would check. It moves like something that wants to look natural. It reveals just enough to keep us watching and not quite enough to force our hand. Whether you buy that story or not, it's a compelling lens that turns a faint, fast traveller into a case study in how an alien scout could cross a solar system filled with eyes, leave a wake of measurements and debates and disappear, mission accomplished, while we keep saying the safest word we know, comet. From the mainstream scientific perspective, the simplest story still fits the most facts. 3I Atlas is a natural interstellar comet, doing comet things in ways that are unusual, but not unprecedented. Start with its path. The object was flagged by NASA's Atlas survey and immediately pegged as unbound, on a hyperbolic in-and-out flyby, so it's a visitor from elsewhere, not a captive of our sun. Its closest swing to the sun sits safely around 1.5 times Earth's distance, and it never comes closer to Earth than roughly 1.8 times that distance. That geometry explains why it's faint, fleeting and scientifically irresistible, all without invoking intention. Then there's what it's made of, which is where the headlines got loud. James Webb didn't see a cold, inert rock, it saw a living coma, gas and dust streaming off the nucleus, with carbon dioxide leading the mix, water and carbon monoxide present, even tiny grains of water ice mixed in. The coma is asymmetrical, brighter on the sunlit side, which is exactly what you expect when one face warms first and vents more. That chemistry is odd for our homegrown comets, but it's comfortably explained if 3I Atlas formed in a colder zone of its birth system where carbon dioxide freezes readily, or if its ices were altered by radiation over an immense journey between the stars. Strange is not the same as artificial. Independent Earth-orbiting data agree. Well before perihelion, NASA's Swift Observatory caught the ultraviolet signature of hydroxyl, the telltale product of sunlight cracking apart water vapour, when 3I Atlas was still far enough out that most comets stay quiet. From that glow, researchers inferred a water outflow on the order of a fire hydrant per second. On paper, that sounds dramatic. In context, it's exactly what carbon dioxide-rich layers and sun-warmed icy dust grains can produce at long distances, and it dovetails with Webb's picture of a coma that's simultaneously CO2-heavy and still carrying water. One telescope found the breath, another spelled out the recipe. Both are seeing the same natural engine. A different vantage point gave a reality check on the visuals. From Mars orbit in early October, ESA's ExoMars Trace gas orbiter stacked short exposures and pulled out a faint fuzzy glow, a real coma around a pinpoint heart. No sculpted panels, no crisp edges, just the gauzy halo of gas and dust that wraps an active nucleus. That Mars side view matters because it confirms the coma from a second angle and helps teams compare how the sunward face brightens relative to the rest, again aligning with simple diurnal heating rather than deliberate thrusting. What about motion that can't be blamed on sunlight and gases, the infamous non-gravitational acceleration that made Oumuamua such a puzzle? This is where calm analysis cuts through the hype. For 3I Atlas, astrometric studies comparing thousands of sky position measurements to pure gravity orbits have so far not turned up a sustained, unexplained push that demands exotic physics or propulsion. Any slight deviations appear consistent with normal cometary outgassing and torques, exactly what you'd predict for a venting, spinning nucleus. That's the opposite of a smoking gun. Radio silence also argues for the ordinary. The SETI Institute's Allen Telescope Array swung toward 3I Atlas right after discovery, checking for the kinds of narrowband radio tones that scream transmitter. Nothing artificial has been reported. No beacon, no coded carrier, no structured ping hiding in the noise. Silence doesn't prove nature, but in a case like this, it's one more piece that fits the comet picture and leaves the craft narrative with no direct support. If you gather the evidence the way most planetary scientists do, a consistent picture emerges. The orbit is interstellar and well-behaved. The coma is real and chemically intriguing. The asymmetry tracks sunward heating. The early water activity can be driven by icy grains lofted from the surface. The drift in the orbit is, at present, explainable by venting rather than by engines. And there are no detections of engineered signals. In short, the data say rare visitor with exotic ices, not undercover machine. That's why major outlets and experts keep reiterating the same message even as social feeds ignite. By what we've measured so far, 3I Atlas is a natural comet. None of this is a dismissal of wonder. Quite the opposite. The counter case is exciting because it widens the map of what comets can be. If other planetary systems build small bodies with carbon dioxide forward recipes, then every interstellar comet we catch becomes a lab for exoplanet chemistry. No starshade or distant probe required. That's a revolution in slow motion. Each new visitor writes a new chapter in a field book we didn't even have before 2017. The scientist's stance isn't don't dream. It's measure first, dream on solid ground. And on the ground we have today, 3I Atlas is a natural, extraordinary piece of elsewhere. Mysterious enough to study hard, not mysterious enough to reclassify as a ship. If a future analysis finds something unambiguous, a persistent, direction-changing thrust that can't be tied to vents, a resolved structure that isn't dust and ice, a repeating radio tone with artificial modulation, the consensus will change. Until then, the conservative, evidence-led reading is the responsible one. 3i Atlas is teaching us about the cold chemistry of another star's nursery, and the most amazing part is that we can read that story at all. That alone is mind-bending enough. What makes James Webb's look at 3i Atlas such a turning point isn't just that it saw gas and dust, it decoded a recipe we've almost never tasted before. In one sitting, Webb's spectrograph found a coma where carbon dioxide is in charge. Water and carbon monoxide are present, and even tiny grains of water ice are floating in the mix, with the outflow brighter on the sunlit side. The measured carbon dioxide to water ratio sits near 8:1, among the largest ever recorded for an active comet, and those fingerprints were taken on August 6, 2025, when the object was still a comfortable 3+ Earth-Sun distances away. In plain English, from far out, 3i Atlas is breathing like a comet, but with a chemistry few of us expected. That single dataset tells us this visitor was built in conditions very unlike the freezer our own comets grew up in. Tie that to the independent water story and the picture gets even stronger. Days before and after Webb's look, NASA's Swift telescope caught the ultraviolet glow of hydroxyl, the calling card of water vapor split by sunlight, and inferred a water loss rate on the order of a fire hydrant every second, at a distance where many comets still sleep. Put together, the two views say, yes, there's water, but 3i Atlas is still overwhelmingly carbon dioxide-led. That combination is unusual for our backyard and instantly broadens the catalogue of what a comet can be in other star systems. This is where the implications ripple outward. Comet chemistry is a map back to the nursery. A carbon dioxide forward breath suggests formation near a carbon dioxide ice line in its birth disk, colder and more distant from its star than the zones that feed most water-rich comets here, or long exposure to radiation that reshaped the ices over eons between the stars. Webb's detection of a sunward-enhanced jet adds a physical anchor to the chemistry. The day side is where the action is, as warming frosts vent and loft icy grains. That doesn't prove anything exotic. It proves that 3i Atlas preserves pieces of an environment our solar system didn't sample as richly. Suddenly we're not just guessing how other disks freeze their gases, we're measuring it directly in a visitor's breath. It also reframes the first two interstellar visitors we met. Oumuamua looked dry and puzzling. Borisov behaved like a classic comet but was unusually rich in carbon monoxide. Now 3i Atlas arrives with strong water activity far out in a carbon dioxide heavy coma. 3 stops, 3 different recipes. With Webb, that diversity isn't a headline, it's a data set you can plot, compare and build formation stories around. That's why planetary scientists keep calling this object a time capsule. It locks in a chemical history from another star's neighbourhood that we can't recreate in any lab. The knock-on effect for future missions is immediate. If weird is normal for interstellar comets, you want eyes that can pounce early and follow through up close. Webb's result is already being used to tune what we hope to see from other vantage points, like the Marside images that confirmed a real diffuse coma, and to set priorities for the next wave of comet hunters. Europe's Comet Interceptor, launching in 2029 to wait in deep space, was designed with surprises like this in mind. It will sprint toward a freshly discovered target, ideally pristine, maybe even interstellar, and split into multiple probes to sample gas, dust, and fields from different angles. Webb's chemistry gives mission planners a preview of the kinds of volatile cocktails we might encounter, and the instruments we'll need to separate them cleanly. On the discovery side, the era of one-off visitors is ending. The Vera C. Rubin Observatory's Sky Survey is coming online to flood us with new finds, turning our handful of interstellar objects into a real population. Instead of arguing over a single strange ratio, we'll have dozens to stack and compare, which means we can finally ask statistical questions. How common are carbon dioxide-led comets? How often do we see early water? Which mixtures correlate with size or speed? Webb handed us the blueprint for what to measure. Rubin is about to supply the sample size. There's a deeper, quieter payoff as well. Prebiotic chemistry, the stuff that sets the stage for life, depends on what ices and dust grains carry across the cold parts of space. Seeing carbon dioxide dominate with water present and sulfur-bearing traces like OCS in the mix tells us that some star systems ship different starter kits into their inner regions than ours did. That challenges simple assumptions about where certain molecules are made, how they're stored, and how readily they can be delivered to young worlds. In other words, 3i Atlas isn't just a postcard from another system, it's a care package list. And finally, Webb changed the tempo of how we do this science. Before, a visitor would blaze in, we'd scrape together whatever light we could, and most of our conclusions would lean on models. Now, with a single observing window, we can read the gas directly, track which side is more active, and compare those findings against other platforms, from Mars orbiters to small ultraviolet telescopes, almost in real time. That multi-instrument chorus is what turns weird into understood. It's also how we'll catch the next one earlier, point the right eyes faster, and ask sharper questions the first time around. 3i Atlas taught us that the universe's cookbook is bigger than we thought. Webb made sure we could finally read it. If there were ever a moment for a whisper from the dark, this would be it. A rare interstellar visitor, bright enough for our best instruments yet distant enough to be safe, is sailing through the inner system. So the obvious question was asked almost immediately. Is 3i Atlas saying anything on purpose? Within a day of its confirmation, the Allen Telescope Array in California began scanning, led by SETI scientists who specialize in catching artificial radio tones that nature almost never makes. They went after the classics first, ultra-narrow-band carriers that would look like needle-thin lines in frequency space, drifting smoothly as the object moves, and popping up only when the telescopes point at the target and disappearing when they nod away. That on-off cadence is the standard reality check for cutting through human-made interference. Early updates from the SETI Institute described exactly this kind of monitoring, narrowband searches alongside checks for natural emissions like the hydroxyl lines that glow when water is being broken apart in the coma. As the scans rolled on, the public messaging stayed careful and clear. There were no detections of engineered signals, no propulsion plumes, no structures, nothing that would pass the bar for technology. SETI's own explainer on 3i Atlas laid it out plainly. Interesting comet, unusual chemistry, zero evidence of a machine. That doesn't make the listening pointless, it makes it scientific. A null result is still a result, especially when the search is tuned to things we'd expect technology to use, like razor-thin radio tones that carry lots of information with very little power. What exactly are they listening for? Imagine taking a radio and sliding the dial across billions of tiny channels, hunting for one hairline sliver that stubbornly refuses to be random. Real techno-signatures are expected to be extremely narrow in frequency. Think the width of a piano string compared to the whole keyboard, because narrow signals are energy efficient and stand out against the broad, messy hiss of nature. As 3i Atlas moves, any true signal would gently drift up or down the dial in a predictable way. SETI instruments chase that drift in software, compensating for the object's changing line of sight speed and the Earth's rotation, and then test whether the tone vanishes when they point away and reappears when they return. That on-off test is the simplest way to reject local interference from cell towers, satellites, or your neighbour's microwave. Radio's only half the story. There's a growing push to check for optical technosignatures too, laser flashes or narrow spectral lines that would be unmistakable if someone were using light to communicate. A recent technosignature study focused specifically on interstellar objects like 3i Atlas shows just how potent this is. Even a modest laser, on the order of a single watt, would pop out in ground-based spectra at a few astronomical units, appearing as a pin-straight spike against the comet's otherwise smooth rainbow of light. Teams have demonstrated pipelines for this kind of search with real telescope spectrographs. If a beam were riding along with 3i Atlas, it would be hard to hide. So far, no one has reported such a spike from 3i Atlas. Instead, early optical and infrared observations have emphasized natural fingerprints, carbon dioxide dominating the gas, water and carbon monoxide present, plus the subtle signs of tiny ice grains and dust, doing what comet dust does. Those are the ingredients you expect to see, even if the proportions are new to us. That natural chemistry story, together with the lack of any structured radio tone, forms the backbone of the not a craft case you keep hearing from mainstream astronomers. It's also worth understanding why radar is not the magic bullet here. Planetary radars like Goldstone can ping near-Earth asteroids with exquisite precision, but 3i Atlas never comes closer than roughly 1.8 times Earth's distance from the Sun, hundreds of millions of kilometers away. At that range, the radar beam spreads, the return is vanishingly weak, and the experiment becomes impractical. In short, we can't sonar the spaceship even if we wanted to, because the geometry isn't on our side. That's why the search leans so heavily on passive listening and spectroscopy instead. Meanwhile, the listening is becoming more collaborative and more creative. Public-facing SETI events have discussed how citizen telescopes and professional arrays can coordinate, pointing networks of small optics to watch the coma while big dishes sweep the radio spectrum, so that if anything odd appears at one wavelength, others can immediately check. The point is to build a layered net. Radio, optical, infrared, each with its own way to shout, "That's weird," and summon the rest. What would actually count as a "we got it" moment? There are a few gold standards. One is a narrowband radio tone that persists across multiple telescopes at different locations, drifts in exactly the way an onboard transmitter would, and vanishes on command when receivers look off target. Another is a laser line that stays pencil thin, repeats in a pattern, or shows sidebands, the telltale fingerprints of modulation. A third would be polarization or pulsing that carries information and tracks the object through the sky. And beyond signals, a genuine morphological detection, a resolved structure that isn't dust or ice, would be decisive. None of these have turned up for 3i Atlas, but these are the benchmarks the community has set, and they're not shy about sharing them because clarity helps separate science from wishful thinking. There's also the messy reality of Earth noise. Our own planet is loud, especially in radio. Airplanes, Starlink-style constellations, ground stations, and countless gadgets can spray interference across huge swathes of spectrum. That's why modern SETI work uses strategies like multi-beam receivers to see if a signal arrives in only one beam, which is suspicious, on-off cadence, and simultaneous observations from different sites to veto local junk. A recent multi-telescope study outside the 3i Atlas context showed how powerful this redundancy is at killing false positives. Those same tactics are exactly what you want when the target is faint, fast, and surrounded by hype. If you're keeping score at home, the tally today is straightforward. Radio monitoring began quickly and continues when geometry and scheduling allow. No artificial narrowband signals have been reported. No optical laser lines have been announced, despite the fact that even modest beams would stand out in the kinds of spectra astronomers are taking. The chemical voice we have heard, carbon dioxide in the lead, water and carbon monoxide along for the ride, sounds like a cold-born comet, not a transmitter. That doesn't kill the dream. It just means the burden of proof hasn't been met. For your visuals, you can make this chapter sing without a single equation. Show a simple radio waterfall plot. Most of it is fuzzy static. Then a mock hairline appears, drifts smoothly, vanishes when the telescope looks away, and reappears when it returns, explaining that this is what a convincing signal would look like. Cut to a spectrum strip with a razor-thin optical spike drawn in, captioned, "What a 1-watt laser would look like at a few astronomical units." Then contrast both with the real story. the broad molecular bands and natural lines Webb and ground-based spectrographs actually see, end on the SETI explainer card that says, plainly, no detection so far, with a short note about why null results matter. It's honest, it's thrilling in its own quiet way, and it leaves room for the next frame in case the universe decides to whisper back. If you really want to move 3I Atlas from odd comet to engineered craft, the proof has to clear a very high bar. Think of it as 3 pillars, each strong enough on its own. First, motion that can't be faked by nature. Astronomers already account for tiny pushes from venting gas and dust when they fit a comet's orbit. If, after weeks of precise sky position measurements, there's a persistent nudge left over that won't go away, even when you let the models include sunward jets and spin-related torques, that's a red flag. We've seen how this works in practice. The famous case of Oumuamua showed a statistically significant extra push, detected only because the astrometry was so careful. For 3I Atlas, the same test applies around and after its close pass by the Sun. If the trajectory bends in a way that can't be matched by our outgassing models tied to what we actually measure coming off the object, the craft case gets teeth. Second, an energy and mass budget that doesn't add up. We're not guessing about what 3I Atlas is releasing, we've measured it. James Webb's spectrum showed a coma rich in carbon dioxide with water, carbon monoxide, carbonyl sulfide, and even tiny water ice grains, with activity enhanced on the sunlit side. Separately, ultraviolet data captured the unmistakable glow from water breaking apart, implying a solid water output when the visitor was still far out. If the path ever demands more thrust than those measured gases and grains can plausibly supply, even letting the models be generous, that mismatch would be a siren. In other words, if the push implied by the orbit is bigger than the push you can get from the stuff we know is venting, something else is doing the pushing. Third, a deliberate signal. The cleanest winds here are narrow engineered beacons, a razor-thin radio tone that drifts exactly as you'd expect from a transmitter riding 3I Atlas, or a pencil line laser feature in an optical spectrum that blinks or carries modulation. Modern techno-signature searches are built for this. They look for ultra-narrow lines, check that they switch off when the telescope nods away, and repeat the detection at multiple sites to kill terrestrial interference. Optical searches do something similar with spectrographs, where even a faint, well-aimed laser at a few astronomical units would stick out as a ruler-straight spike against a comet's smooth rainbow. If anything like that were seen from 3I Atlas, and verified independently, it would end the debate in a single plot. There are also supporting exhibits that, while not as decisive alone, would stack the odds. Resolved hardware is the obvious one. Plates, struts, plumes, anything with edges. The reality is that we're resolution limited. Even Hubble's crisp images can only place an upper limit on the nucleus size. They can't cleanly pull the solid body out of the glow at these distances. Mars orbit shots caught a faint, real coma from a unique vantage, but no nucleus or tail structure, exactly what you'd expect this early. To actually see engineered geometry, you'd want a spacecraft flyby or something truly enormous. Until then, no panels in the pictures simply reflects the physics of blurry small things very far away. Thermal and reflectance tricks are another angle. Unnatural steady heat at wavelengths that don't track sunlight and sublimation, or mirror-like glints repeating with a clockwork pattern, would be suspicious. And while it's a long shot, there are even ideas for catching artificial illumination, city light levels on outer world surfaces. The underlying point is the same. Engineered light looks different from nature. If 3I Atlas ever showed a stable, modulated glow, not tied to its spin or the sun, that would push the needle. What, concretely, would the "we got it" moment look like to a viewer at home? Imagine a before-after orbit plot where the predicted natural path, based on the gases we actually measured, diverges cleanly from the real path. And that divergence keeps growing in a way that can't be patched by changing the assumptions about vents. Picture a radio waterfall where a hairline tone slides smoothly with the comet, disappears when the dish looks away, and reappears on return, and then the same thing shows up at a second observatory thousands of kilometres away. Or a spectrum from a big optical telescope with a single dead straight line that repeats and carries simple on-off coding. Any one of those, nailed down and replicated, would flip 3i Atlas from mystery to message. There's also a timing angle. Around closest approach to the Sun, activity should spike, and that's when small jets produce the biggest natural kicks. That's why the post-perihelion months matter so much for the motion test. Once the coma settles, any lingering, steady nudge is harder to blame on venting. It's also when telescopes can listen and stare with less solar glare. If a narrowband radio whistle or laser line is going to show up, this is the window where we're most sensitive and least likely to confuse sunlight-driven chaos with intention. Meanwhile, planned follow-ups, from Earth, from Mars orbit, and even a brief look by ESA's Jupiter-bound JUICE spacecraft, had extra camera angles to check for consistency. And because extraordinary claims need extraordinary process, the path to proof has to be transparent. That means releasing the raw and calibrated data, listing every check against interference and processing artifacts, and inviting independent teams to replicate the result. The community learned this the hard way with famous false alarms in Radio SETI. The gold standard now is redundancy, open methods, and confirmation by instruments with totally different failure modes. A genuine techno-signature riding with 3i Atlas would sail through that gauntlet. Where does that leave us today? With a clear checklist and clear expectations. If 3i Atlas suddenly displays a sustained, unexplained change in its path that outgassing cannot carry, if its light splits to reveal a deliberate carrier tone or a laser line that repeats, or if any camera, Earthside, Marsside, or deep space resolves structure no coma can fake, the story changes overnight. Short of that, the measurements we do have, a CO2-rich coma with sunward enhancement and early water activity, fit a natural if exotic comet, born in a very different freezer than ours. That's already thrilling science. The door to something more is open, but it only swings on evidence that won't collapse when everyone else points their instruments at the same thing. If you're determined to argue that 3i Atlas is almost 100% an alien ship, you start with a stack of oddities and you don't let up. You point to James Webb's reading of a breath that's upside down by local standards, carbon dioxide in charge with water and carbon monoxide along for the ride, and you call that a design choice rather than a frozen accident. You point to the sunward biased activity, the way the day side seems to act like a focused blowtorch, and you say, that's how controlled venting would look if your propellant was stored as deep frozen ices and released with gentle heat. You add the early water story hydroxyl glowing in ultraviolet, when 3i Atlas was still far from the sun, implying a fire hydrant level water output, and you frame that as a timed wake-up, not just sunlight on fragile ices. In this telling, every surprise is a breadcrumb, then you layer in the choreography. The geometry is almost theatrical, a safe sweep through the inner system, closest to the sun in late October, never anywhere near Earth, bright enough for flagship instruments but too faint to trigger public panic. From Mars orbit, cameras catch a real, diffuse coma, confirmation from a second world that this visitor is active. From Earth orbit and the ground, spectra pile up. If you wanted to probe a technological civilization sensor web without being intercepted, you could hardly script it better. Give them something to study, keep them busy, and leave before anyone can do more than argue. You can even make the speed sound deliberate. 3i Atlas is racing through at tens of kilometers per second, fast enough to be unbound, quick enough to defy any thought of a chase. To a believer, that's not just dynamics, that's tradecraft. A scout comes in hot, Spaceship rides a sun-skimming arc for maximum data, and exits on schedule, leaving only questions in its wake. But here's the reality check that refuses to budge. The measurements we have today all live inside nature's playbook. The distances and dates line up with a normal interstellar flyby, perihelion about 1.5 Earth-sun distances, closest Earth approach around 1.8 Earth-sun distances, no threat, no dramatic pass. The chemistry, while exotic by our standards, has straightforward origins if 3I Atlas formed in a colder zone of a distant disk or had its ices processed by radiation over an interstellar trek. The sunward blowtorch is exactly what you expect when one face warms first. None of that demands engineering. The loudest counterweight is silence itself. The Allen telescope array began listening almost immediately, sweeping for the kind of razor-thin radio tones that are the cheapest, clearest way to shout, "We're here." As of now, there's no credible artificial signal, no repeating beacon that passes the on-off, and multi-telescope tests techno-signature hunters use to kill earthly interference. Listening will continue, and it should, but a null result keeps the burden of the proof on the extraordinary claim. So what would it actually take to move 3I Atlas out of the odd comet box and into the engineered column without caveats or winks? First, motion that refuses to be explained away. Astronomers already fit tiny natural pushes from outgassing into a comet's orbit. If, after the perihelion fireworks settle, there's a persistent, direction-changing nudge that can't be matched by any combination of measured gases, vents, and spin, the needle jumps. Second, an energy budget mismatch. We're not guessing about what's venting, we've measured carbon dioxide, water, and more, and we have ballpark production rates. If the trajectory ever demands more thrust than those numbers can plausibly supply, you've got a problem the comet model can't fix. Third, a deliberate signal. A pencil-thin radio carrier that tracks the object and reappears at multiple observatories, or a laser line in an optical spectrum that repeats or carries modulation. Any one of those would be decisive. Short of that, the fairest conclusion is both less sensational and more profound. 3I Atlas is already rewriting the margins of our comet textbook. Webb's spectrum alone widened the recipe book for small bodies born under other suns. Swift's ultraviolet detection showed water, waking up far out. Marside imaging gave us a second camera angle on a genuine coma. This is how a field matures, not with a single reveal, but with many instruments, many angles, many data sets that converge on a story sturdy enough to carry our wonder without collapsing into wishful thinking. If you want to end on the strongest possible version of the almost 100% argument, you can. Just be clear with your audience about where the line sits. Say that 3I Atlas checks several boxes a disguised scout would check: unusual chemistry, directional activity, early awakening, careful geometry. Then say the part that makes the video honest. Extraordinary claims need extraordinary evidence, and the most powerful tests are already underway. Until those tests deliver a smoking gun, the object in our frame is best described by the label that fits the data we actually have. A rare interstellar comet, carbon dioxide forward and gloriously inconvenient for our old assumptions, brushing past our star and taking its secrets with it. That's not a letdown. It's the kind of mystery that leaves the door open and tells us exactly what would have to walk through it to change everything. And that's where we leave it tonight, standing at the edge of the known, watching 3I Atlas glide back into the dark. A faint smudge, a wild itinerary, a breath that doesn't read like anything from our neighbourhood, and a chorus of instruments leaning in to listen. James Webb peeled the light apart and showed us a recipe that flips our expectations. Swift heard water waking up long before most comets stir. Cameras around Mars teased out a soft halo from tens of millions of kilometres away. Radio dishes listened for a whisper that never quite came. Whether you wear the natural comet badge or you're convinced we're looking at a cleverly dressed visitor. You have to admit this. We are living through one of those rare moments when the universe gives us a puzzle big enough to stretch our imagination and clear enough to test with data. Think about how many things had to line up for us to even tell this story. A survey telescope in the south spots a speedy stranger. Orbital dynamics say it's not staying. The timing puts it within reach of our best eyes. Webb is awake, Mars has orbiters pointed the right way, spectrographs around the world are hungry. And then the object itself is cooperative, active but not blinding, close but not dangerous, mysterious but not mute. It's almost as if the cosmos handed us a lab experiment and said, "Here, Try your tools on this. That alone is breathtaking. What we've learned will echo for years. If 3I Atlas is just a comet, no small just, by the way, it still tears open the idea that comets everywhere must look like our own. It tells us other stars stock their freezers with different ices, different balances, different surprises. That means the ingredients delivered to young world can vary wildly, and so can the stories those worlds go on to tell. If, on the other hand, you're persuaded by the choreography, the early wake-up, the sunward push, the careful geometry, then this has been a masterclass in how a civilization might travel without leaving fingerprints. Either way, we win. Either way, our understanding deepens. There's also something tender and human woven through all of this. We built machines that can catch the faintest breath of a traveller from another sun. We taught them to split light like a prism and hear whispers in the radio night. We trained them to look not only at planets and stars, but at the small wanderers, the messy ones, the ones we used to call dirty snowballs, and move on. And when one of those wanderers came from elsewhere, we didn't shrug, we didn't look away. We turned the full attention of our species toward it and asked the oldest, bravest question we know. What are you? Maybe that's the part that matters most. Not whether 3I Atlas is a craft or a comet, but what our response says about us. We're a species that gets curious before it gets afraid. We are a species that points cameras and radios and far-flung telescopes at the unknown and says, explain yourself. We argue, we test, we revise, we argue again. That's science. That's wonder with a method. And tonight it feels like a promise we're making to our future. Whatever passes near our star, we will meet it with open eyes. So here's what I'd love from you. Tell me where your head and heart landed after this journey. Do you see a natural time capsule frozen in a distant nursery and blown our way by chance? Do you see a disguised scout choosing the perfect moment to test our sensor web? Or do you hold both possibilities at once, letting the data steer you as it arrives? Drop your take in the comments, one sentence or a full theory. If you caught your own images, if you ran your own spectra, if you listened with a backyard dish or stitched frames from a small telescope, share that too. This channel is full of people who love the night sky. Let's make this one of those threads a stranger would smile to read. If this deep dive spoke to you, tap like so the algorithm knows to send more curious minds our way. If you want more stories like this, more cosmic mysteries, more careful detective work, more late night wonder, hit subscribe. Ring the bell so you don't miss the next investigation. I read your ideas, I learn from your corrections, and I keep a running list of questions you want answered. Your voice shapes where we go next. And for those who stay to the very end, thank you. You are the ones who sit with the whole story, not just the headline. You're the ones who remember that the universe rarely gives us clean answers on the first pass, that patience and attention are superpowers. Whether 3I Atlas turns out to be an exquisite natural relic or the most successful camouflage in cosmic history, the gift it already gave us is clear. It made us look harder, think sharper, and feel smaller in the best possible way. When you step outside tonight, take a second and look up. Somewhere out there in the black between stars are countless objects just like this one, already on their way, already carrying the fingerprints of places we will never see with our own eyes. Somewhere out there are more messages written in ice and dust and sunlight. We won't catch them all, but now you know that sometimes on an ordinary night, with the right tools and the right attention, one of them writes its name across our sky and we get to read it together. Until the next mystery crosses our path, keep your curiosity warm and your conclusions cool. Keep asking good questions, keep looking for the faint things, and remember, even if the universe whispered nothing but silence this time, silence is an answer too. It tells us how to listen better. It tells us what to try next. It tells us that wonder isn't waiting at the end of the story. It's flowing through every step we take to tell it. Thank you for watching, for thinking, for feeling the weight of this with me. Share this with someone who needs a moment of awe. I'll see you in the next one. And wherever you fall on the great debate, one thing is certain: 3i Atlas made our world a little bigger.